discuss much yet about this part. So this is still in the axial deformations, the statically indeterminate structure. So sometimes you have, suppose some structure that is attached both ends on the wall, and if you see there are some elongations in between, but since we are having the walls that is attached to the structure, that the total elongations we assume it will be a zero. So what will happen if we have this is basically we can cut, for example, if we look on the element 1, we can cut anywhere on that element 1, and basically making the, if we have the internal force, suppose that this F1 is the force in the element 1. If you look on this part itself, this becomes somehow, it becomes determinate because we cut this, and suppose that this is becoming the forces, the dominant force. So F1 becomes just like similar to external force, but of course this is internal force. This is just our assumption. So we can make the structure statically determinate by cutting the element 1 like that. So we select the F1 as our redundant internal force, and then what we can do is we can cut this element 2 and 3 in a similar way, so that we can have for example, now we need to cut this part and this part. So when we cut the section B, we are going to have, so suppose that this is the still using the F1 as our so-called external force. So suppose that this is having the F1 right here, and then it has this reaction force, and now we have another force that is basically from the element 2. Okay, and by doing so we can also take the section C, we can cut, and taking reference with the F1, and then cut the element 3. So suppose that this is 1, this is 2, 1, 2, 3. Maybe make it better if I just draw here is the F2. Okay, what we care much is we are making the internal force as external force. Okay, so by this cutting, we make the because what we want is we have this PB in between 1 and 2, and PC in between 2 and 3. We would like to know the PB and PC. So based on what we have from the internal force, taken up the equilibrium, we can make the first one is the, let's say we say this will be F2 plus PB. This is equal 0. And from the second picture, we can have, this is PB, sorry. So negative F1 plus PB plus PC plus F3 is equal 0. Okay, and now we can rewrite this. And first of all, since what we did firstly in this method, okay, the first time we cut the F1, we take F1. This is internal force, but we treat F1 as external force to help finding the other part of the force. Okay. So we are going to write F1 as in the terms for F2 and F3. For example, suppose that we know PB and PC, then we can write F2 in terms of F1 and PB, and F3 we can write in terms of F1. Okay, so we treat F1 as the external force, although F1 is actually internal force. Okay, this is to help in solving the system equations. Okay, and now what we have on all the elements, since they are attached on the walls, well, we can know, for example, the other systems to solve this force, to get into to solve this. Okay, to solve this, what we need is the assumption from the elongations. Okay, so total elongations, because it's on the wall, then elongation 1 plus elongation 2 plus elongation 3 will be 0. Right? And each elongations we can write in terms of the force, F1, F2, F3, using the FLAE. Okay, so maybe we can write first the elongations. Well, let me write the original description of the elongation. Is basically, so every time you have the axial deformation, you can always start writing down this formula. Okay. The F is basically, you can using the F from this part, from these equations. L usually described within this L1, L2, L3. A usually described in the picture, maybe they have different diameter. And E usually described whether they are using the same E or not. And basically that's it for E. So we can state for each one of E, we can write, or let me write just E1 is F1 L1, right? Divide A1 E1. Okay, let me just write with 1 subscript, and then 2 A2 E2 and 3. And then the total should be equal to 0, and we say that this is what we call as a compatibility equation. The equations that supposedly based on some descriptions or some assumptions that we add to solve the equations. Because if we don't have these assumptions, we are not going to solve this, right? Because we have unknown variables that still not sure. Okay, now every part for F2 and F3 we can exchange with our system of equations. Okay, so first we can exchange the F2 by taking the F1 minus PB from our system of the force, and F3. right? And then all of this we can write in this E. So we can substitute back to the E. Let me write here. So we can substitute to here all of this. So F1, L1, A1, E1 plus okay, and this will be equal to 0. Let me resize this. And basically we can solve this F1, okay? We can solve this F1 and we can get the F2, we can get the F3, okay? And from this F1, we can get the stress for each one of them, taking it into the, well, it depends on the case. If you want to calculate the stress immediately, you can do that. You can just exchange F1 and A becomes the sigma. But here, you need to know the F2, the whole thing for F1 and PV. So I think you can solve the F1 first when you get the F1. Then you can get the F2 and F3 immediately. Okay. So basically what this says is F1 becomes the only unknown variables, right? The L1, L2, L3 is supposed to be given in the information. A1, E1 also usually given in the information. So basically this is the last discussion that we call this a basic force method. Okay. So usually basic force method, we are having the forces as our variable. Okay. But either the displacement method or the force method, they both works with the when we have the system of equations and we have the compatibility equation. So basically this is just a normal substitution as long as you know how to define the equilibrium. Okay. So if you can define the equilibrium, you can define the compatibility equations, you can substitute. Maybe you can start from this force, substitute there, or we can start from the equilibrium and then get into here, similarly. Okay. So either you are having force and then you solve E, or you solve E and then you get the forces as this one. Okay. You get the force and you get all the stresses. Okay. And after we get the stresses, we can also get the displacement. For example, this UB, we can get the UB because we imagine that this is going to be the right side. Then we can imagine that UB is actually equal to extension of element 1, right? So we can also add here that UB is element 1, the same. And UC is basically, because we have the total elongation is 0, when we have UC, which is element 2 is longer and element 1 also longer. But what happened in element 3, because it is attached to the wall, we can say the elongation and in the element 3 it becomes negative. It becomes reduced. Okay. It has reductions. So this will be equal to negative element elongation 3. And we can calculate E1 and E3 from our calculations here. Okay, basically, after you get the force, you can get everything. Okay, you can get everything. So you need to solve from this. Okay. And I think to solve this, I think you are going to use just normal linear equations. Okay. You can substitute eliminations, but sometimes maybe the number having a decimals. Okay? So if you have a calculators and you can set your calculators to solve system of equations, I hope you can use that. Okay. But I think no need, because you can just plug in the numbers and compute the F1. Okay, I think you will get, eventually you will get, as long as the number is correct. Okay, and then the planars and in elastic axial, I will skip that part. Okay, so we are basically focused on determinate structure and indeterminate structure in a simplified way, focusing more on the displacement and basic force method. Okay. And basically you can set up different way if you want. Practically in this example, we are using F1. This is what we call as a redundant force, which is, it will be, we are forcing this force, we are forcing this force to be appear in all of our equations, like we did in our system. So we are, this is actually internal force, but we treat this like an external force. We can do the same thing if we cut this and taking maybe this is F3 and then this is on the left. So we can have the F3 as our redundant force, which means we can solve the system and use and find the F3. Okay. That's the same way, Okay, so let's move to torsion. Tomorrow I will review again the chapter 3 example and exercises for more problems. But now let's continue to the torsion. I have mentioned a little bit, I think last week, of the torsion. So torsion, basically, the differences between axial deformation and torsion is basically on the way the force will be exerted. Okay, in the axial deformations, we have the axial forces, and then it will given the elongations to the system. But in torsion, we have something we call the torque. Okay, torque is something that can be twisted. And what is the result? The result is you will have a twisted angle. Okay, you have a twisted angle. You have the normal stress in the axial deformation. In torsion, you have the shear stress, okay, because of the torque. And you have extensional strain, you have the shear strain, you have Young's modulus of elasticity, or in torsion, you have a shear modulus, okay? So this is some analogy between these two that could be helping you out, because their formulations basically similar. Okay? Their formulation is similar, but the way we visualize is a little bit, if you are not careful, the torsion can be really confusing because it's not elongated. And if you see here, because we are dealing with something that is rotating, so the elongations will be the angle, the difference in the angle. So if we twist it, there will be some differences. The point will be displaced and moved out from the system, and it will create a different angle. If we could, perhaps if we could see more clearly, we could have these differences. Okay, if we twist it, you see that the straight line becomes a little bit, having some like a gradient like that. And you see that in some way we could compare the the twisted structure and the original structure, and we could see the difference in the angle. And we call it the twisted angle. The more clear differences we can see if we have this is the square cross section. You can see that it's going to be really twisted, but in the circular, it's much more smoother on the surface. And when you compare, one note that we can write here is that a circular shaft solid or tube or tubular, when it is subjected to torsion, the cross section or each cross section it remains plane and simply rotates. About the axis. Of the member. Okay, so look at the axis here, in between of these two. So they are not going anywhere. They are not going to be bent in the pure torsion. So they will be simply rotates, and it remains in the plane. This remains in the plane. And because of that, we can develop the theory for the torsion for circular members. And if we imagine the cylinder, if we have a deformations because of the torsion, if you see from this part here, okay, we have this picture. Suppose that we have some weight on both sides, but it is on this circle. So which means that this is having some force P. This is having another force which is pretty equal, and this is pretty much going to be twisted because of these two forces, and we have the angle that is going to be our twist angle, and you will see that the ABCD point will be displaced, and we have a new point for A, B, C, and D. So the original point is moved out, and we see this is going to be twisted. It will be twisted. So this is after deformation. Okay. Now we can write some notes here. Our fundamental assumption so axis remains straight. Okay, and this is pretty much important, and remains inextensible. So the length is not going to be extended. Okay. Every cross sections. This is similar to what I have written before. Every cross sections remains plane. And perpendicular. So there's nothing bend in the axis. So it's only pure torsion, okay? Although in the real life there will be some slightly different perceptions. But in the theory, to make it a pure torsion, we need to assume that every cross section will be a plane. So if we cut, it will be, if it is a tube, so if every cut in the y-axis, we are going to have a circle. Okay? The shape will be the same, okay, for every cross section. And radial lines remain straight. This is aligned with the axis. And radial as the cross section. So straight and, sorry, I think make it. And radial as the cross section rotates about the axis. So radial line is the lines in the circular system. So it's still the same. Nothing changed. Nothing geometrically observations. They are practically the same. Okay. So the only way that we can see the changes is the point in between the virtual lines. Okay. Now let's get into the method or the equations that we can have. So we can start from the strain displacement equations. Okay. So first of all, by taking the strain displacement analysis that we have before, we are going to have the sign conventions. The sign convention. Let me start from here. Okay, the sign conventions. So the longitudinal axis is the x-axis. Okay, if you could see from that point of view. And then we have the origin, the axis. And then we are going to twist and giving a torque. So first, we are giving a positive torque in this way. Okay? This is sign convention for the internal torque. So let me define the torque first. Maybe let me draw on the left here. Okay. So positive torque or T of x is actually a moment that act on cross section at x in right hand rule. About the outer normal to the cross section. And in the cross sections, there will be another opposite torques that is indicated by this picture here. We have this, and this is supposed to be the right hand above the outer normal. And if we are used to look at that is as our internal torque, then the other will be canceling out. Okay? So if there is the internal torque, there will be another torque that is in the opposite direction. Just like moment, when you cut, you have moment here, moment there. But in this way, we are having the torque in terms of the circular bar. Okay? And then another thing is the positive angle rotation. Or we are using psi. So this is rotation of the cross section at x in a right hand rule about x-axis. As mentioned in this figure. So we start from so axis, we are by default, if we observe, we can start from taking this right hand. Actually, you can try in the opposite conventions. If you're consistent, you will have the same conclusion. But to help analyze, because I think the difficulty in the terms of torsion is imagine the how it moves. Okay? Compare with the chapter 3, the axial, we can imagine it's extended or maybe reduced. But here it's rotated, like it's not easy to be drawn. Okay? Sometimes maybe the angle will be really small, and then we need to imagine how it will be rotated. So that will be, I think, difficult to see. So now, after we have all these assumptions for the sign, now we need to combine the torque and the rotations in the mathematical descriptions. Okay, now let's say this part here that has the delta, we are going to observe this small part, and then we cut, and then we can zoom in a more clear image. So let's say we have this. Okay. So suppose that we have a shaft between the cross section at x and the delta x, okay, and we have all the points, we have all the twisted angle, the side. So then we can write the shear strain. If you remember the shear strain, so let me write here, relation between the torsional deformation or the twisted angle and the shear strain the shear strain we have learned a little bit from the previous sections, right? So the shear strain in terms of the x and the radius, this will be pi over 2 minus the angle between if we look at here, we have Q asterisk, R asterisk. Let me here, okay, and the S. So QRS, and we could see this is the angle. And basically, the shear strain is this small angle here, which is, this is, we imagine as a pi over 2. So this will be pi over 2 minus the QRS. And this will be the angle of the S prime R asterisk and S asterisk here. This is the S prime, R asterisk and S asterisk. Okay. So this is the shear strain. Okay. Okay, now we can describe the shear strain. And then we also remember that the shear strain is very small. And when the angle very small, we can approximate the angle by the tangent. Okay, so this is like a triangle. Okay, it's like a triangle. So we can draw this as a triangle. This is so this will be the shear strain. So then this strain we can develop using the tangent. Okay, using the tangent from the, or we can just write directly using the, when the limit of this length approaching to 0, so becomes a very, very small. And we can exchange the angle for the twisted angle here. We can take this as a delta of psi, the delta of the twisted angle, and then we can have this rho as our in the radius inside the circular part. So we can actually describe the, let me write here, the S asterisk and S prime. This is a sector, so it's actually here. So let's say this is the, and here is the delta psi. So the sector here, this is actually, so if we have the radius rho, then this will be rho delta of psi, right? So we can change the S prime, the S asterisk, the arc length as rho delta theta, over the R prime S prime is the delta x. And by definitions, in calculus, the delta meaning the differences or the derivative. Okay? And the rho is just a constant, so rho so this will be rho d psi dx. And so we have the strain displacement equation as the shear strain equal rho d psi dx. The d psi dx, we can also write this as a twist rate. And the shear strain, it can be also distributed on every point. If we cut them into several points, it will be distributed on every point possible in the circular bar. As example, if we have a solid bar like this, then we are going to have all possible strain in every point. And of course, in the outer part, this will be the maximum shear strain. So we're going to have a break and we're going to continue. Okay, now we continue. So basically, the first part on the torsion, we're going to imagine that the circular bars or the torsion will be linearly elastic. Okay, linearly elastic, which means all the torsion, the deformation itself will behave in linear behavior. Okay. So let me go through this part. Okay. So torsion of linearly elastic circular bars. Okay, so if we look at the, let me first start with the picture here. So we have the torsional deformations as we mentioned before. So let's take out an element of the typical points. Suppose that this is the sections. This is we cut this part, okay, and we get this. Which, if you remember, we are going to have a typical stress strain formulations. If we look at all the strain or shear, stress and strain, there will be another distribution. So there is always or shear stress not only on cross section but there is always another shear stress that acts on the radial planes. Means that we all have this shear stress. Okay? So not always in terms of the cross section, but also in the radial planes. Okay, let me add one more just to help out the description. So here is another description. Relationship between the torque and the shear stress. So there will be an increment, okay, of the force defined by the shear stress. Okay? So suppose that we have this small elements dA for the cross sections, and we can define the increment of shear force and it will be equal to the shear stress tau multiplied with the area. Remember that the stress is basically force divided by the area, so we can use the increment of the shear force as the tau and then dA. And then the torque, the incremental force or incremental torque as in the force is basically the radius multiplied by the shear force or the increment of the shear force. So we can write down the resultant torque as, let me write here. Let me take this smaller, and that is the resultant torque. Okay, is basically the integrations on the rho and then the F, or because we can observe the area as our point of integration, we can write down the dF as tau dA. Okay? Tau dA. So it means torque is all the summations of the small increments, okay? Of the small increments. So we calculate all in terms of the integrations. Okay, now from this resultant torque, we can also correlate with the stress strain behavior using the shear modulus. I don't think we need this. I think we can erase. So the strain displacement, as we get from the previous example, we have a rho and then d psi dx, that is the twist rate. And then using the Hooke's law, which is the tau equal to G and strain, shear strain. And then since we have the strain displacement equations, we can use these equations and changing the shear strain so that we can get this descriptions of the shear stress is equal to modulus multiply the rho and twist rate. So this gives you a general descriptions or shear stress distribution at a typical cross section of a linearly elastic bar. Okay. So remember, in this part, in these topics, we are going to have a linearly behavior, okay? Elastic behavior. So if the torsion bar is homogeneous or uniform, or G is a constant, then the shear stress will vary linearly according to the distance of the radius. That is basically what it says about this G, rho, and then d psi dx. With the maximum shear is on the outer surface, like here. Okay, the tau max is on the maximum radius. So we can write down the torque resultant from the previous part is the integration with respect to A, G, rho, d psi dx, and then dA. So G is constant, so we can take G and then take out the twist rate and then integrate it only with respect to A, because all of this is not A, so we can factorize. And the only way that is vary is on the radius. So rho squared dA. So this part is actually we call as the polar moment of inertia. Or we call this as and there are only two possibilities, whether it is going to be solid circular bar or you have a whole hollow bar. So it could be inertia or polar moment of inertia. There's only two possibilities. The first one is pi r with power of 4, and this is always true for all solid. Okay. Or you can write in terms of diameter. So 2 with power of 4, 16 multiplied by 2, 32, right? This is for solid cross section. Or if there is a hollow, then we can subtract. Okay? We can minus the radius. So the polar moment, it will be pi over 2. This is or we can use the diameter. Okay, basically subtraction of the r. Okay, this one here. Okay, so the O, it will be for outer radius, the I will be in the inner. Okay, this will be for hollow cross section. And then we can simplify the descriptions. So from that descriptions, we can write this become T, G, the psi dA, and then inertia. And we can rewrite this as just simply as that. GIP is, we call this as torsional rigidity. So this is derivative form of torque twist equation. And then important to also apply which one is the correct sign convention. Okay, which one is the positive torque. So remember that the positive torque always produce positive twist rate, or the angle, positive angle. And how to know that? Using the right hand rule. Okay, and then combining the equations previously we have the tau is G rho, right? So combining this, we can have so from here we have G is T over IP, right? So from this part, we can have T rho over IP for the tau, for the shear stress. So this is, we call the torsion formula. So remember, all of this valid. Okay, so this is valid if G is constant on all cross sections. Okay. Now the tube, it can be also considered as, for example, if the hollow part we can exchange with another solid. So this is solid, maybe steel, and inside maybe aluminum, or maybe inside is steel, outside is aluminum. It can be done as and works like that as well. So basically, what you need to think first in the torsion, we need to know what is the inertia, the polar inertia. And polar inertia will be always in between those formulations. Either it's solid or having a hollow. And then we can take the tau formulations for the torsion formula. Tau is T rho over the inertia. Okay. We can use this. Rho is the radius. Okay, now let me give you an example. So suppose that we have the torsion bar. It has the aluminum shell and the core, steel core. So both of them have their own G. They have their own shear modulus. And it has this dimension. And I think this is in the, not in SI units. It is in the US metric system. But it is works the same. We have the torque directly. So it's mentioned that torque is the 10 kip inch, and it has total length 50. The diameter for the outer shell is 2 inch from the center, and 1 inch for the inner diameter, right? So first, we need to determine the maximum shear stress for steel and for aluminum. So imagine that the shear max is on the outside, right? So both of them have different description. Okay, suppose that this is the steel. So that's the center. This is the center. Okay. So this part here, perhaps I will make it a little bit higher. This is for steel. This is the distribution. So suppose that this is the tau steel max. And here, perhaps the aluminum may be on that point. So let's say this is the aluminum tau max, okay? So since we are only care about the maximum, so it means we are going to concentrate on each one of the diameter. So we can write the tau as for the steel. So steel is GS rho, and then the twist rate, which is the rho is between the steel is 1 inch, or the rho will be half. And for the aluminum, it's GA rho, and this will be starting from 0.5, right? This is starting from 0.5 until 1 inch. Okay. And if we substitute these expressions on the definition of the torque, okay, so we can substitute all the tau. So because this is going to be combining steel and aluminum, so we are going to combine and make it into the total torque. Okay, total torque is 10 kip, so we can equal this with the steel and suppose that this is area for steel, rho squared dA plus the aluminum. Okay. Or we can simply write, because they have the same twist rate, and this will be the inertia. This is also inertia, but different element. So GS IPS, polar moment for steel, plus this is polar moment for aluminum. So this is the torque. So the twist rate, we can divide the torque with this GS IPS plus GA IPA, which we can get from all the information we have. Okay, so T is 10 kip inch, and GS is here 11, and GA is 4,000, right? So 11,000, 4,000, and IP based on the radius or diameter. So this will be 10 kip. Kip is kilopound, so kilopound inch. The G will be for steel is 11,000 KSI, kilopound square inch. This will be inertia. For the steel is solid, 0.5 inch with power of 4. Make it longer. Actually, you can write directly. This is just to show you that how we can develop our equation. You can go directly to this formulation if you want. So this will be 4 KSI pi over 2 . And now we have a hollow for the aluminum from 1 inch power 4, 0.5 inch power 4. Calculations, we get this is equal to 1.434 multiply 10 with power of -3 radian per inch, and we can calculate the shear stress maximum for steel. This is at rho equal negative or 0.5 inch, so we get from this part here GS rho since we get the twist rate, we can combine everything and we can calculate each one of them. This is around 7.89 KSI. And for aluminum, this is maximum at rho equal 1 inch. So this is GA rho 4,000, 1 inch, and 1.43. This is equal 5.74 KSI. And the total twist angle, we can get the total twist angle from the integrations of the twist rate, or we can just simply multiply with the L. So the length is just a 50, so we can just multiply this radian inch with 50 inch, and we get 7.17 radian. Okay, I think this is quite straightforward. Basically, what you need is the torsion relations between the tau and the twist rate equations in terms of torque. Okay. And by the way, I think we will have a quiz on chapter 3 next 2 weeks, okay? Not next week, next 2 weeks, so we have time. So tomorrow I will review again chapter 3 in the exercise. And next week we can have another review on chapter 3 for the Tuesday class. For 1 hour class, we can have a review. And after that, that will be quiz on chapter 3. So 2 weeks, okay? So now is 6th of May. So 7, and then we have 14, so 21, okay, 21. So May 21, there will be quiz on chapter 3. But in the Monday class, we will continue the torsion, okay, the torsion until finish. And maybe at the end of the before the final exam, we will have one more chapter about beams, okay, about beams. Okay, now let's just summarize what we have so far. So we have the torsion formula and the maximum shear stress formula. So this is summary. Summary of the torsion theory for homogeneous linearly elastic bars. So we have the torsion formula. If we have a variations in terms of x and rho, we can have that, and we can also have the maximum shear stress formulations. Remember that this is for homogeneous or linearly elastic member with circular cross sections. And sometimes all the torque, the modulus, and the polar inertia, it can vary with the x. It can vary with x. And we can have also a variation in terms of radius. For example, if we look at this radius is different for each sections, each part of the axis. So we have the Rx here, which is the variation in radius along x-axis. And we have a distributed torque for every part of them. So we can have a torque twist equation. You can write here. So we can have a torque twist equation. Where the angle, this is a total angle of twist, or total twist angle. Or we can write this psi is psi of L minus psi of the origin point. And the angle of rotations, we can have, let me put here, this is the angle of rotations at cross-section X. Now we can start with the psi at the origin, plus we have the integrations, because there will be variation in terms of X, and that means that every cross-section will have different radius, which means we need to have another variable that need to be assigned. So this is a dummy variable. Dummy variable to help working with these integrations for locating the cross-sections between 0 and X. So in summary, if we have different variation in radius, that means we can evaluate, but with another integrations for the radius itself. But in uniform, so if we take a look here, we have uniform torsion member. Which describe as this, and we can start from taking the total angle, and then the twist angle is equal okay, and then T is constant, and torsion member is uniform, as you can see from the picture. Then we can have this, the angle, and this will be, so remember, okay, I will write what you have in the axial deformations as elongations is F, L, A, E. So this pretty much works the same. The difference is the elongation part. In axial deformations, you have F, right? L, and then A, area, and then the modulus, the Young's modulus. In the torsion, in axial deformation, it's E, elongation. But in terms of torsion, it will be the angle. this is the torque, like F, same length. We have the modulus G, and this is E, and this is the inertia, and this is area. So inertia is kind of describing the area, which is basically determined by the radius or diameter, the same as this one. Okay? So similar, you could feel similarity, and how we can use is basically also the same. Okay? The difference is how we can visualize the twisting descriptions of the axis. Okay, that's basically the difficult part is that part. Okay. Okay, let me give you an example. Okay, how to get this correctly. By looking at this tube, so we have shaft, tubular shaft. We have the outer radius and the inner radius, R1 and R1 over 2. And it is made of a material with shear modulus G and subjected to the torques T0 for figure 1A, the top one. And determine expression for the tau maximum for this 1A, determine the twist angle for the same reasons. And if the same torque applied to solid circular shaft in figure 1B, the bottom picture, and what is the radius of the solid shaft? Okay, what is ratio of the weight of the solid shaft to the weight of one? So we are going to discuss the ratio of this two tubular. Okay, so we have two tubulars. So we are going to solve the first tubes, the top one. We can start with so first is determine the expression of tau max. So for A, the tau max will be the torque max and then multiply with the radius divided by, or sometimes we can use R or rho, but I will just use R. This is divided by the polar moment inertia. The polar moment, if you see from the picture, is basically pi over 2. We have the outer radius is R1 and inner radius is R1 over 2. So we can write as that. And simplifications, we have so 16, 32, so half minus 32, this will be 15 R1 with power of pi R1 with power of 4. Okay, that's the inertia. So you look using this inertia, and the torque is T0, R is R1, 15 over 32 pi R1 with power of 4. Then we get, this will be 32 TO, this will be 15 pi R1 cube. Okay, you can cancel the R1. And that is for A. For B, the angle shaft for picture 1 is T0L and then G and then the inertia. So we can exchange using the same inertia. So this will be 32 TOL and this will be 15 pi G1 or G because it's constant G, R1 with power of 4. Okay, that's it. And number C, or let me write number C is here. Okay. Number C, R2 such that the maximum shear stress tau max will be producing the same. Okay, so T2 will be equal to the T1 will be equal to the T0. So the tau max for 2 is T max, and then R2 divided by the inertia for picture 2. So T max will be T0, R2, and the inertia, we have this only the solid, so this will be pi over 2, R2 with power of 4, or this will becomes 2 TO, we have pi R2 with cube. Okay, so that's the tau max. And then since we want to get the R2, then since we have the same tau max, so tau max 1 equal tau max 2, this will be 32 TO 15 pi R1 cube. This is 2 TO pi R2 cube. Okay, so we can cancel this, that, and we get the R2 is we can also cancel this 2 with 16, so it will be 15 over 16 cubic roots R1, or 0.97 R1 for R2. Therefore, the weight between 2 and 1, we can take this into this ratio pi R2 squared L, and the circular on 1 is having a hollow, so we have R1 squared minus R1 over 2 squared L. The same length, we can cancel this pi and L, so we get 4 over 3 R2 over R1 squared, which is we get from here. So the R2 over R1 is 0.97, so we can substitute to there, so we can have 1.277. So the tubular shaft has a quite advantage over this solid shaft, because the solid shaft, it has 28% more than the tube. So using the weight ratio, we can see the advantage on the hollow structure. So I think I will end up until here. We're going to see the next week for the torsion. Tomorrow we are going to have example on chapter 3.
And I think I will skip a few parts and I will focus more on the practical applications. So more on the theory I will skip for the most part. And basically similar to chapter 3, we are going to have the statically determinate and indeterminate structure, but in torsions, okay, in torsions. So if you get the idea on chapter 3, you will have also the similar expressions on the chapter 3.